Hello there, and welcome to Sleepy Science. Rain feels ordinary, but what if I told you that every drop falling outside your window began its journey days ago, possibly over an ocean thousands of kilometers away? What if the sound you find relaxing is actually a complex acoustic pattern your brain recognizes as safe? And what if most raindrops never even reach the ground? Tonight, we're not just listening to rain. We're breaking down what it really is, how it forms, how it behaves, and why your mind responds to it the way it does. Because once you understand rain, you'll never hear it the same way again. Rain feels ordinary because we see it all the time. It falls from the sky, hits the ground, and disappears. Most people never stop to think about where it actually begins. But here is the surprising part. Rain does not start in the clouds. It starts much earlier, far away from where it finally falls. The drop that lands near you may have traveled across oceans and continents before you ever noticed it. Rain is not random water falling from nowhere. It is the result of a long and precise natural process. If even one step in that process changes, rain would not form the way it does. So the real question is this: how does something so common begin in such a complex way? To understand rain, we need to go back to the very beginning, long before clouds even appear in the sky. Rain is part of something much bigger called the water cycle. The water cycle is the continuous movement of water around our planet. Water does not stay in one place. It moves from oceans to air, from air to land, and from land back to oceans again. This process has been happening for billions of years. The water you see in rain today may have once been in a river, a glacier, or even inside a living creature. Nothing is wasted. Nothing is new. It is the same water being reused again and again. The water cycle has three main stages: evaporation, condensation, and precipitation. Each stage depends on the others. If one stops, the cycle breaks. That means no clouds, no rain, and no fresh water for plants and animals. So if rain is only one part of this cycle, what exactly starts the entire process? The true starting point of rain is evaporation. Evaporation happens when liquid water changes into water vapor, which is an invisible gas. This happens every single day on oceans, lakes, rivers, and even wet soil. When water molecules gain enough energy, they move faster and escape into the air. You cannot see this happening, but it is constant. Even a small puddle slowly disappears because of evaporation. The largest source of evaporation on Earth is the ocean. Huge amounts of water rise into the atmosphere every second. This rising vapor is the raw material that later forms clouds and rain. Without evaporation, there would be no moisture in the air. And without moisture, rain would be impossible. But evaporation does not happen on its own. Something must give the water molecules the energy they need to escape. So what provides that energy? The main source of energy for evaporation is the sun. The sun sends heat to Earth every day. When sunlight reaches oceans and lakes, it warms the surface water. Heat adds energy to the water molecules, causing them to move faster. When they move fast enough, they break free from the liquid and rise into the air as vapor. This process happens more quickly on hot days because there is more heat available. That is why clothes dry faster in the sun. The sun is like a giant engine that powers the entire water cycle. Without its heat, evaporation would slow down almost completely. That means clouds would not form properly, and rainfall would decrease. So the next time you see sunlight shining on water, remember that it is quietly preparing the next rainfall. But once the vapor rises, what makes it turn back into liquid again? Most of the rain that falls on Earth begins in the ocean. The ocean holds about 97% of all water on the planet, so it is the main source of moisture in the air. When sunlight heats the surface of the ocean, the top layer of water begins to warm up. As the water warms, some of its molecules gain enough energy to escape into the air. This change from liquid to gas is called evaporation. Salt does not rise with the water vapor. It stays behind in the ocean, which is why rainwater is fresh and not salty. Every second, huge amounts of water leave the ocean this way. You cannot see it happening, but it never stops. Even at night, evaporation continues, just more slowly. So when you feel rain on your skin, remember that it may have started as ocean water far away. But when that water rises, what does it actually look like? When ocean water changes into vapor, it becomes invisible. Many people think water vapor looks like the white mist from a kettle, but that is not correct. The white cloud you see from boiling water is actually tiny liquid droplets, not true vapor. Real water vapor cannot be seen. It mixes completely with the air around us. The air you breathe always contains some amount of water vapor, even on a clear day. On humid days, there is more vapor in the air, but you still cannot see it. This is important because clouds are not made of vapor. They are made of tiny liquid droplets that formed after vapor cooled down. So when water leaves the ocean, it does not rise as visible steam. It rises as an invisible gas. That means something else must happen before we can see clouds forming in the sky. What carries this invisible vapor upward? As the sun heats the surface of the earth, it also warms the air above it. Warm air becomes lighter than cool air. Because it is lighter, it rises upward. This rising movement is called convection. When warm air rises, it carries water vapor with it. Think of it like an elevator made of air, lifting moisture higher into the sky. This process happens over oceans and land. Areas that are hotter usually have stronger rising air currents. That is why tropical regions often have more clouds and rain. The rising air does not move in a straight line. It mixes and swirls as it goes up, spreading moisture through different layers of the atmosphere. Without this upward movement, water vapor would stay near the ground and rain would not form properly. But as the air climbs higher, the environment changes. So what happens to warm, moist air as it rises further? As warm air rises higher into the atmosphere, the temperature begins to drop. The higher you go, the colder the air becomes. This happens because air pressure decreases with height, causing the air to expand and cool. When the rising air cools, the water vapor inside it loses energy. Cooler air cannot hold as much moisture as warm air. At a certain point, the air becomes full or saturated with water vapor. When that limit is reached, the vapor begins to change back into tiny liquid droplets. This process is called condensation. These tiny droplets gather together and start forming clouds. So cooling at higher altitudes is the key step that turns invisible vapor into something visible in the sky. Without cooling, there would be no condensation, and without condensation, there would be no clouds. But how do these tiny droplets grow large enough to eventually fall as rain? Condensation happens when water vapor in the air changes back into liquid water. This change takes place when the air cools down enough that it cannot hold all the moisture anymore. Warm air can store more water vapor, but cold air has a lower limit. When that limit is reached, the extra vapor must turn into tiny liquid droplets. This is a physical change, not a chemical one. The water molecules slow down as they lose heat energy. When they slow down, they move closer together and begin sticking to each other. That is how liquid water forms again. You can see condensation on a cold glass on a hot day. Water droplets appear on the outside, even though you did not pour water there. The same thing happens in the sky, just on a much larger scale. But here is the important question. Where do those tiny droplets first begin to form? Water vapor cannot easily turn into liquid on its own. It needs a tiny surface to gather around. In the atmosphere, there are countless microscopic particles floating in the air. These particles are called condensation nuclei. They can be tiny bits of dust, grains of sea salt from ocean spray, pollen from plants, smoke, or even pollution. They are so small that you cannot see them without special tools. When air cools and reaches saturation, water molecules begin attaching to these particles. Without them, condensation would be very difficult in normal conditions. That means clouds would not form as easily. The sky may look clean and empty, but it is actually full of invisible particles helping rain to begin. So the next time you look up at a cloud, remember that it started with something as small as dust. But why does water need these tiny particles at all? Water molecules are very small and move freely when they are in vapor form. For condensation to start, the molecules must come together and stay connected. However, in open air, it is harder for them to gather without something to hold on to. A condensation nucleus gives the water molecules a starting point. When vapor touches one of these particles, it sticks to it and begins forming a tiny droplet. More and more molecules attach, and the droplet slowly grows. Without this surface, water molecules would need very cold temperatures to join together on their own. In normal atmospheric conditions, these particles make the process much easier. That is why condensation happens even when temperatures are above freezing. So even though the particles are extremely small, they play a huge role in forming clouds. Now imagine billions of these tiny droplets forming at the same time. What do they create? When millions and millions of tiny droplets form around condensation nuclei, they gather together in the sky and create what we see as clouds. Each droplet is microscopic, much smaller than a raindrop. A single cloud can contain trillions of these tiny droplets floating close together. They are so light that rising air currents can keep them suspended. That is why clouds do not immediately fall as rain. From the ground, a cloud may look thick and solid, but inside it is mostly empty space filled with tiny droplets and air. Light reflects off these droplets, which is why clouds appear white. When more droplets form and pack closer together, the cloud becomes darker. So a cloud is not a single object. It is a massive collection of countless tiny water droplets working together. But how do these microscopic droplets combine to become heavy enough to finally fall as rain? A cloud may look soft and solid from the ground, but it is not a single mass of water. It is made of trillions of tiny liquid droplets floating close together in the air. Each droplet is so small that it would take thousands of them lined up to match the width of a single raindrop. These droplets are light enough to stay suspended because of rising air currents inside the cloud. The air moving upward balances the slight pull of gravity on each droplet. That is why clouds can stay in the sky for hours without raining. Even large clouds are mostly empty space filled with air. The droplets are spread throughout that space, constantly moving and interacting. So when you see a cloud, you are looking at an enormous collection of tiny water particles working together. But if they are so small and light, why do clouds look bright and white instead of invisible? Clouds appear white because of the way light interacts with the tiny droplets inside them. Sunlight may look clear, but it actually contains all colors of the spectrum. When sunlight enters a cloud, it hits billions of small water droplets. These droplets scatter the light in all directions. Because the droplets are larger than air molecules, they scatter all colors of light almost equally. When all the colors mix back together, your eyes see white. That is why most clouds look bright during the day. When clouds become thicker and contain more droplets, less light passes through. This makes them appear gray or dark before rain. So the color of a cloud tells you something about how much water it holds. But brightness alone does not cause rain. Something must make those tiny droplets grow larger. So how do microscopic droplets turn into heavy raindrops? Inside a cloud, the tiny droplets are constantly moving because of air currents. As they move, they sometimes bump into each other. This is called droplet collision. When two droplets collide, they may stick together instead of bouncing apart. Each successful collision creates a slightly larger droplet. Larger droplets fall a bit faster than smaller ones, which increases the chance of hitting more droplets below them. This starts a chain reaction inside the cloud. The process is not perfectly smooth. Some droplets miss each other and some break apart. But over time, enough collisions happen for certain droplets to grow much larger than the rest. This is an important turning point. A cloud full of tiny droplets alone will not produce rain. Growth through collision is necessary. But what exactly happens when these droplets combine and become heavier? When droplets collide and stick together, the process is called coalescence. Coalescence means small droplets merge to form one larger droplet. As this continues, some droplets grow big enough that rising air can no longer hold them up. Gravity begins to pull them downward more strongly. At first, they fall slowly, but as they descend, they may collect even more droplets along the way. This makes them heavier and faster. Eventually, the droplet becomes large enough to fall out of the cloud completely as rain. Coalescence is one of the main reasons rain forms in warm clouds. Without this merging process, droplets would remain too small to fall. So rain is not simply water falling from a cloud. It is the result of countless tiny collisions and mergers happening high above you. But once a droplet begins to fall, what controls how fast it reaches the ground? Inside a cloud, droplets do not all grow at the same speed. Some stay very small, while others slowly become larger through repeated collisions. As droplets move through the cloud, they pass through areas with different temperatures and moisture levels. In some regions, extra water vapor may condense onto them, making them grow even without hitting other droplets. In other areas, collisions happen more often, which speeds up their growth. The larger a droplet becomes, the easier it is for it to collect smaller droplets in its path. This creates a cycle where growth increases the chance of even more growth. Over time, a few droplets become much bigger than the rest. These larger droplets are important because they are the ones most likely to turn into rain. But even a growing droplet cannot fall immediately. It must reach a certain point where it becomes heavy enough to overcome the forces holding it up. For a droplet to fall from a cloud, it must pass a weight threshold. This means it must become heavy enough that the upward air currents inside the cloud can no longer support it. Small droplets are extremely light. Rising warm air can easily keep them suspended. That is why clouds can exist without raining for long periods. As droplets grow through condensation and collision, their weight increases. Eventually, the upward push from the air equals the downward pull of gravity. When the droplet becomes slightly heavier than the rising air can hold, it begins to descend. This is the critical moment when cloud water starts turning into rainfall. The exact size needed depends on the strength of the updrafts inside the cloud. Stronger updrafts require larger droplets to begin falling. So once that balance shifts, what force actually pulls the droplet downward? Gravity is the force that pulls the droplet toward the ground. Gravity acts on everything with mass, including tiny water droplets. Even while droplets are floating in a cloud, gravity is still pulling on them. The reason they do not fall right away is because upward air currents push against that pull. When a droplet becomes heavy enough, gravity wins the struggle. As it starts falling, gravity continues to accelerate it downward. However, the droplet does not keep speeding up forever. Air resistance pushes upward against it, slowing the acceleration. Soon, the droplet reaches a steady falling speed called terminal velocity. From that point on, it falls at a constant rate. Gravity is the main driver that turns cloud water into rainfall. But this leads to an interesting question. How large does a droplet need to be before gravity truly takes control and sends it falling to Earth? A typical raindrop is much smaller than most people imagine. Many drawings show large drops, but in reality, most raindrops are between 0.5 and 4 millimeters in diameter. A light drizzle may contain drops closer to 0.5 millimeters, while heavy rain may have drops around 2 to 3 millimeters wide. Very rarely do raindrops grow larger than about 5 millimeters. If they become too large, they break apart before reaching the ground. To understand how small that is, picture the width of a grain of rice. Many raindrops are close to that size or even smaller. Even though they seem tiny in your hand, they are large compared to the microscopic droplets inside clouds. That small increase in size makes a huge difference in weight. So if most cloud droplets are too small to fall, why do those tiny droplets stay suspended in the first place? Small droplets float in clouds because they are extremely light and are constantly supported by rising air currents. Inside a cloud, warm air moves upward. This upward motion pushes against gravity. When droplets are very small, the upward force of the moving air is stronger than the downward pull of gravity on them. Because of this balance, the droplets remain suspended instead of falling. It is similar to dust particles floating in a beam of sunlight inside a room. They are not truly weightless, but the air movement keeps them from settling quickly. In clouds, this process happens on a much larger scale. Billions of tiny droplets are held up at the same time. However, as droplets grow larger and heavier, this balance begins to change. Something else starts affecting their fall as they move downward. What slows them down once they begin falling? As a raindrop begins to fall, it does not move through empty space. It moves through air, and air pushes back against it. This pushing force is called air resistance. Air resistance works in the opposite direction of motion. When a droplet falls downward, air resistance pushes upward against it. The faster the droplet falls, the stronger the air resistance becomes. At first, gravity makes the droplet speed up, but as its speed increases, air resistance also increases. This creates a balance between the two forces. The shape of the droplet also affects how much resistance it experiences. A flatter droplet meets more air and feels stronger resistance than a small round one. Air resistance plays a key role in controlling how fast raindrops travel. Without it, rain would fall much faster and hit the ground harder. So what happens when gravity and air resistance finally balance each other? When gravity pulls a raindrop downward and air resistance pushes upward, there comes a point where the two forces become equal. When this happens, the droplet stops accelerating. It continues falling, but at a constant speed. This steady speed is called terminal velocity. For small raindrops, terminal velocity may be only a few kilometers per hour. For larger drops, it can reach up to 20 to 30 kilometers per hour. Even at that speed, air resistance prevents them from becoming dangerous. Terminal velocity depends on the size and shape of the drop. Larger drops fall faster because gravity has more mass to pull on, but they also face stronger air resistance. This balance keeps rainfall steady and controlled. So now that we understand how fast raindrops fall, another question appears. What happens to them during their journey from cloud to ground? Raindrops of different sizes fall at different speeds because gravity and air resistance affect each one differently. Small droplets, like those in light rain or drizzle, fall slowly because they are very light and air resistance easily slows them down. Medium-sized raindrops fall faster because their weight allows gravity to overcome air resistance more quickly. Large raindrops fall even faster, but only up to a certain limit, because air resistance grows stronger as they get bigger. This is why a heavy rainstorm feels much more intense than a light drizzle. Even though all the drops start from the same cloud, they reach the ground at different times and speeds. This difference creates a layered effect in rainfall, where some drops seem to fall gently while others hit faster. Understanding this shows that rain is not uniform, but a complex mix of droplets behaving in different ways. But while falling, raindrops do not just travel straight, they interact with each other. As raindrops fall, they can collide with other droplets in the air. These collisions happen more often in heavy rain, where many drops are close together. When two drops collide, they may merge into a larger drop, increasing their size and speed. Sometimes collisions cause smaller droplets to break apart, producing even more drops. Collisions also affect the path of the drops, making them wobble or move slightly sideways. This is why raindrops are never perfectly straight when they fall. Collisions play a critical role in determining which drops become large enough to reach the ground as heavy rain, and which remain small or evaporate before landing. The movement and interaction of falling droplets create the rhythm and sound we hear during rainfall. But in very heavy rain, an additional change can happen to these falling drops. In very heavy rain, some large raindrops can break apart before reaching the ground. This happens because as a drop grows, air resistance flattens its bottom and stretches it into a shape that is less stable. When it becomes too large, the drop cannot hold together, and surface tension is not enough to keep it intact. The drop splits into smaller droplets while still falling. This breakup helps regulate rainfall, preventing enormous drops from falling and causing damage. It also contributes to the variation in raindrop sizes you feel on your skin. Drop breakup is a natural consequence of the physical limits of water. Even though it may seem random, it follows the same principles of gravity, air resistance, and surface tension every time. But when a raindrop first forms and begins its descent, it starts with a very specific shape. Raindrops are spherical at first because surface tension pulls the water molecules together into the shape with the smallest surface area for a given volume. A sphere is the most efficient shape for a droplet to form naturally. When a droplet is small, the forces of gravity and air resistance have little effect, so it maintains this round shape perfectly. The spherical form allows the drop to stay intact while rising or falling slowly. As the droplet grows larger, airflow starts to deform it, flattening the bottom and creating a more oblong shape. But initially, the sphere is crucial because it allows water molecules to stick together and survive until they reach a size that can overcome air currents. The perfect sphere is nature's starting point for every drop of rain. Once droplets leave this shape, what happens to their journey next? As raindrops fall through the air, they are affected by the airflow around them. Small droplets maintain their spherical shape, but larger ones start to flatten at the bottom. This happens because air pushes upward against the falling drop, while gravity pulls it downward. The combination of these forces stretches the droplet slightly, creating a shape that is more rounded on top and flatter underneath. The faster the drop falls, the stronger this flattening effect becomes. Extremely large drops may even take on a shape similar to a hamburger bun before breaking apart. Flattening affects how raindrops collide with each other and how they scatter light, which is why clouds and rainstorms can look different depending on drop size. This change in shape is an important part of the rainfall process because it determines whether a drop will stay intact or split. But many people still imagine raindrops differently from how they actually look. Many people picture raindrops as tear-shaped, like the classic image in books or cartoons. However, this is not accurate. Small drops are almost perfectly round, and even larger drops are only slightly flattened at the bottom, not pointed like a teardrop. The idea of the tear shape comes from artistic interpretation rather than science. Real raindrops are shaped by surface tension and airflow, not by emotion or symbolism. Even when droplets fall at high speed, they rarely form the long, narrow tip that people imagine. Understanding the true shape of raindrops helps explain why rain falls smoothly, how it interacts with light, and how collisions and breakups occur. So the next time you see rain, remember it is not shaped like a tear. It is a sphere slowly changing under the forces of physics. But what happens to a drop after leaving the cloud but before it reaches the ground? Before a raindrop reaches you, it has a complex journey through the atmosphere. Not all droplets that leave a cloud reach the surface. Some are slowed by strong upward air currents, while others collide and break into smaller droplets. Temperature, humidity, and wind all influence the path of a falling drop. Some drops may start falling but evaporate completely before reaching the ground. This is why light rain can sometimes disappear midair, or why rainfall appears patchy. Every drop is moving through layers of air with varying temperatures and moisture, which can change its size and speed. The journey is not straight or simple. It is a combination of forces constantly acting on the drop. This hidden journey is happening above you every time it rains, often unnoticed. But evaporation can also play a major role while the drop is still falling. In some conditions, raindrops can evaporate while they are still falling, a phenomenon known as virga. Virga happens mostly in dry air where the humidity is low. As a drop falls, the surrounding dry air absorbs some of its water. The smaller the droplet and the drier the air, the faster this evaporation occurs. Sometimes the drop completely disappears before touching the ground. You may see streaks of rain falling from a cloud that never reach the surface. This is virga. It is more common in deserts or high-altitude areas. Virga also cools the air as it absorbs heat from the drop, creating interesting local weather effects like sudden gusts of wind. So even though rain may appear simple from the ground, many droplets never complete their journey. Understanding virga reveals just how delicate the balance is between a drop forming and actually reaching you. Not all rain that begins falling from a cloud actually reaches the ground. There are several reasons for this. One major reason is the presence of dry air below the cloud. As droplets fall through dry layers, they lose water through evaporation faster than they can reach the surface. Small droplets are especially vulnerable because they have less mass and evaporate quickly. Strong winds can also carry them sideways or even upward, preventing them from landing. Even in heavy storms, some raindrops disappear before reaching the ground. This is why rainfall can sometimes be inconsistent, with patches of wet and dry areas under the same cloud. Understanding why some rain never reaches the surface helps explain why deserts can exist near regions with large clouds, and why meteorologists sometimes measure rainfall differently in various locations. This process shows that rain is not guaranteed once it forms in the sky. As raindrops fall through dry air, the process of absorption by the air becomes very important. Dry air can hold more water vapor than already saturated air, which means it will pull moisture from the falling droplets. This happens because water naturally moves from areas of higher concentration, the raindrop, to areas of lower concentration, the dry air. The rate of absorption depends on the temperature and humidity of the air. Hot, dry air absorbs water much faster than cool, moist air. Because of this, smaller droplets often disappear entirely before reaching the ground, while larger ones may shrink in size. This interaction between falling rain and the surrounding air explains why light rain can seem to vanish, and why rainfall intensity is not uniform. It also shows that the atmosphere actively controls how much water actually arrives at the surface. Downdrafts are downward-moving currents of air that occur within clouds or beneath storms. These strong air movements push the air and droplets toward the ground. In some cases, downdrafts can carry raindrops faster than they would normally fall due to gravity alone. They form when cooled air inside the cloud becomes denser and sinks. Downdrafts are common in thunderstorms and can create sudden bursts of rain at the surface. They are also responsible for strong winds during rainstorms because they push air downward and outward as they descend. The presence of downdrafts affects rainfall patterns, making some areas receive heavy showers while neighboring regions remain dry. This is another reason why rain from the same cloud can vary in intensity as it reaches the ground. But moving air is not the only way falling rain changes the atmosphere. Falling rain actually cools the air it passes through. As raindrops fall, they absorb heat from the surrounding air during evaporation, especially if the air is dry. This removes thermal energy from the air, lowering its temperature slightly. In addition, large volumes of rain can displace warmer air, replacing it with cooler droplets from higher altitudes. This cooling effect is why some storms feel noticeably cooler underneath the clouds, even if the sun is shining nearby. The cooling of air can also create local currents, influencing winds and the movement of other raindrops. This effect contributes to the refreshing feeling of rain on a hot day. So every falling raindrop is not just water, it is actively changing the air it passes through. Rain can have a noticeable effect on temperature near the ground. When rain falls, it absorbs heat from the surrounding air as some of the water evaporates, which cools the air slightly. Additionally, rain often comes from higher altitudes where the air is cooler than at the surface. As the droplets descend, they carry this cooler air down, which reduces the temperature at ground level. This is why a sudden rain shower on a hot day can make the environment feel much more comfortable. Rain can also reduce surface temperatures by wetting the ground and absorbing heat from sunlight. The overall cooling effect depends on the intensity of rainfall, the size of the droplets, and the temperature difference between the clouds and the ground. Understanding this shows that rain is not only water falling from the sky, it actively changes the environment around it. But rainfall does more than just affect temperature. It also plays a key role in the life of a storm. Storms are able to sustain themselves because of a continuous supply of warm, moist air. When warm air rises into a cloud, it carries water vapor, which condenses into droplets and releases heat. This released heat warms the surrounding air, making it lighter and causing it to rise faster. The faster rising air draws in more warm air from below, creating a cycle that fuels the storm. This is why thunderstorms can last for hours or even move across large distances. The energy of the storm comes from both the temperature differences in the atmosphere and the moisture being lifted into the cloud. As long as the storm can pull in warm, humid air, it can continue producing rain, wind, and lightning. The process of rising and cooling air is essential for the storm's life. But this rising movement also creates another important cycle inside clouds. Inside clouds, warm air rises while cooler air sinks, creating updraft cycles. These cycles carry tiny water droplets higher into the cloud, allowing them to grow larger as more water vapor condenses onto them. Updrafts help maintain the cloud's structure and keep droplets suspended, until they are heavy enough to fall as rain. In thunderstorms, strong updrafts can lift droplets very high, even forming hail in some cases. The continuous rising of warm air and the sinking of cooler air ensures that clouds remain active, full of energy, and capable of producing sustained rainfall. Updraft cycles are like elevators for water droplets, giving them multiple chances to grow and combine before reaching the ground. Without these cycles, clouds would produce only light, short-lived showers. Understanding updrafts is key to understanding the rhythm and intensity of rainfall. When rain finally starts to fall, it creates a sound that we hear from the ground. The sound is not random. It is produced by the impact of droplets on surfaces like leaves, soil, and rooftops. Larger drops produce deeper, louder sounds, while smaller droplets create a soft, continuous patter. Even the air around the droplets contributes, as moving air creates additional vibrations. The combination of thousands or millions of falling drops generates a rich, natural pattern that can feel soothing or intense depending on the rain. This sound can affect humans and animals psychologically, signaling safety, freshness, or sometimes danger in storms. What we hear is the result of countless droplets interacting with surfaces and the air, creating an acoustic signature unique to each rainfall. Understanding the science behind rain sounds explains why it is naturally relaxing. Raindrops create sound when they hit surfaces because of the energy released on impact. Each droplet carries kinetic energy as it falls, and when it strikes a hard or soft surface, that energy transfers into vibrations in the surface and the surrounding air. These vibrations generate sound waves, which travel to our ears. The size of the droplet, the speed at which it falls, and the type of surface it hits all affect the tone and volume of the sound. For example, a large drop hitting metal produces a sharp, loud ping, while the same drop hitting soil makes a softer, muffled sound. Even leaves and plants create distinctive noises as drops land on them. The variety of sounds created by millions of raindrops gives rainfall its characteristic rhythmic pattern. Understanding this explains why rain sounds different in various places and why it can feel calming or intense depending on conditions. The sounds raindrops make start with the breaking of surface tension. Surface tension is the force that holds the water molecules together at the surface of a drop. When a droplet hits a surface, the molecules at the bottom spread out rapidly, breaking the tension. This sudden break releases energy into the air as tiny vibrations. The effect is like plucking a string on a musical instrument. Energy is released in the form of sound waves. Softer surfaces like soil absorb more of this energy, creating a low, muffled sound, while hard surfaces transfer more energy to the air, making a sharper sound. Surface tension breaking happens incredibly fast, in just fractions of a second, but it is enough to produce the recognizable sound of rainfall. This is one reason why rain can sound gentle and soothing even during heavy showers. But surface tension breaking is not the only visual and audible effect when raindrops land. When a raindrop hits a liquid or soft surface, it can create a splash crown. This happens when the droplet's impact pushes the surrounding liquid upward and outward in a circular shape. The crown is a brief, delicate formation that lasts only milliseconds, but contributes to both the visual effect and the sound of rainfall. Splash crowns are more pronounced when the droplet is large or falling at high speed. They also affect how the water spreads across the surface, breaking the drop into smaller droplets that continue to move. Each tiny secondary drop from a splash crown can create its own microsound, adding complexity to the overall rainfall noise. This interaction between falling droplets and surfaces explains why rain produces layered, dynamic sounds rather than a single uniform pattern. Understanding splash crowns reveals the hidden mechanics behind the beauty of rain. Raindrops hitting soil can trap tiny air bubbles, which also contribute to rainfall sounds. When a droplet strikes the ground, it pushes water into the pores of the soil. Some air gets trapped and forms small bubbles under the surface. These bubbles quickly rise and burst, releasing tiny sound waves into the air. The combined effect of millions of these bursts adds a soft, popping layer to the overall sound of rain. The size and number of bubbles depend on soil type, moisture level, and drop size. Sandy soil creates different bubble sounds compared to clay or soft mud. This process not only affects the sound but also helps oxygenate the soil, which is important for plant life. So each raindrop is creating a small physical effect, in addition to making the rhythmic noise we associate with rainfall. When a raindrop hits soil or water and traps an air bubble, that bubble eventually bursts, releasing energy into the surrounding air as sound waves. The burst happens almost instantly, producing a tiny pop that is too fast for the eye to see but can be heard collectively during rainfall. Each bubble creates its own miniature vibration, and when millions of droplets are falling simultaneously, these small sounds combine to form part of the complex pattern we hear as rain. The size of the bubble affects the pitch of the sound. The smaller the bubble, the higher the frequency of the pop. Larger bubbles produce deeper, lower sounds. This process explains why rainfall is not a single uniform sound but a combination of countless tiny impacts and bursts. Bubble bursting adds richness to the auditory texture of rain, giving it that soothing, layered rhythm that many people find relaxing. But these sounds are also influenced by the surfaces where raindrops land. The type of surface raindrops land on affects the frequency of the sounds they produce. Hard surfaces, like metal roofs or concrete, transfer energy efficiently into the air, producing sharp, high-frequency sounds. Softer surfaces, such as soil or grass, absorb more energy, resulting in lower, muffled sounds. Even small differences in texture, like wet versus dry leaves, can change the tone of the raindrop's impact. These variations in frequency create a natural symphony during rainfall, making it dynamic rather than monotonous. When multiple surfaces are present, raindrops produce overlapping frequencies, which our brains interpret as the rich and calming pattern of rain. This frequency variation explains why the same rain can sound entirely different in the city compared to a forest or garden. Understanding this helps us appreciate the subtle science behind what our ears perceive as a simple sound. Rain sounds differently on metal compared to soil because of how each surface interacts with the falling droplets. Metal is hard and non-absorbent, so raindrops hit it and bounce slightly, creating a sharp, ringing sound. The sound waves travel quickly through the metal, amplifying the noise. In contrast, soil is soft and porous, so droplets sink in rather than bounce. This absorbs some of the energy, producing a lower, softer patter. The moisture level of the soil also changes the sound. Wet soil tends to make deeper, quieter noises, while dry soil produces crisp pops as droplets hit hard patches. These differences explain why the same rainstorm can feel harsh and loud on a rooftop, but gentle and calming in a garden. By understanding the surface effect, we can see that rain sound is not just about the water itself. It is a combination of droplet size, speed, and landing surface. Leaves alter the sound of rain because of their shape, flexibility, and texture. When droplets hit leaves, the water may roll off, drip from edges, or be absorbed partially by the surface. Each of these interactions changes the sound. Broad, flat leaves create louder splashes, while smaller or curved leaves disperse the water more softly. Flexible leaves can bend under the weight of falling droplets, reducing the force of impact and creating muffled, soothing sounds. Water running along leaf veins and dripping from tips produces a delicate, rhythmic noise that is different from the direct patter on the soil below. The combination of hundreds of leaves in a tree canopy creates a multi-layered soundscape, adding variety to rainfall. This is why walking under a forest canopy during rain sounds different than standing in an open field. Leaves act as natural sound modifiers, enhancing the richness of the rain experience. The sound of rain is often described as pink noise because of the way its frequencies are distributed. Pink noise contains all the frequencies that humans can hear, but the energy is balanced so that lower frequencies are louder than higher ones. This creates a soft, even sound that is gentle on the ears. Unlike a sudden, sharp noise, pink noise spreads sound evenly across the spectrum, producing a soothing background hum. Rain naturally generates this type of noise because of the combination of raindrops hitting different surfaces, splashing, and creating overlapping patterns. The resulting sound is complex but balanced, which is why listening to rain can feel relaxing and help people concentrate or sleep. It is different from artificial sounds, but our brains respond to it in a predictable, calming way. This explains why recordings of rainfall are so popular for relaxation and meditation. But to understand this fully, we need to compare it to another type of noise called white noise. White noise is different from pink noise because it contains all the audible frequencies at the same intensity. This makes white noise sound harsh or static-like, similar to a loud television static or a buzzing fan. In contrast, pink noise balances energy so that lower frequencies are louder and higher frequencies softer, which is easier for our ears to process. White noise is random and constant, with no natural patterns for the brain to follow. Pink noise, like rainfall, has subtle variation and rhythm, giving our minds something familiar and predictable to latch onto. That balance between randomness and pattern makes pink noise more pleasant and calming. The comparison helps explain why rain sounds, unlike random noise, can make us feel relaxed instead of irritated. Understanding the difference between white and pink noise shows why natural rain sounds are so effective at calming the mind. The human brain finds patterns in sound calming because it can predict what comes next. When we hear organized, rhythmic noise like rainfall, the brain recognizes recurring patterns in volume, tone, and timing. This predictability reduces mental effort, as the brain does not need to process sudden, unexpected changes. Our neural circuits prefer stable patterns because they signal safety and familiarity. In nature, repetitive sounds like rainfall, ocean waves, or wind rustling through leaves historically indicated a non-threatening environment. This natural response still exists today. The brain interprets these patterns as a signal to relax, reducing stress and anxiety. In contrast, chaotic or unpredictable sounds trigger alertness, releasing stress hormones. The ability of rain to provide a steady, rhythmic sound is why it is often used to help people sleep, meditate, or focus. Recognizing this connection between pattern and calmness reveals the deeper reason rain is naturally soothing. Rainfall activates the parasympathetic nervous system, which is responsible for rest and relaxation in the body. When we hear gentle, rhythmic rain, the brain interprets it as safe and predictable, triggering this system. Activation of the parasympathetic nervous system slows heart rate, lowers blood pressure, and promotes digestion and recovery. Breathing also becomes slower and deeper, which increases oxygen delivery and further calms the body. This is the opposite of the sympathetic nervous system, which handles stress and fight or flight responses. By activating parasympathetic responses, rain helps the body enter a state of relaxation naturally. This physiological effect explains why listening to rain can make people feel sleepy, reduce anxiety, and even improve focus. Essentially, the sound of rain is not just pleasant, it directly signals the body to calm down and rest, reinforcing why humans find rainy environments so comforting. Listening to steady rain can reduce the level of cortisol, the body's stress hormone. Cortisol is released in response to threats or unpredictable events, keeping the body alert and ready for action. When we hear gentle, continuous rainfall, our brain perceives the sound as safe and predictable. This recognition signals the body to slow down stress responses. The parasympathetic nervous system activates, heart rate drops, and breathing becomes more regular. Cortisol levels gradually decrease, which reduces tension in muscles and eases anxiety. Scientists have found that exposure to consistent, calming sounds like rain can lower cortisol within minutes. Unlike sudden loud noises, rain does not trigger a fight-or-flight reaction. This is why people feel relaxed or sleepy during rainfall. The steady sound acts as a natural stress reliever, helping the body and mind recover. But the calming effect of rain is not only about its consistency, it is also about the rhythm the brain can anticipate. Rain creates a rhythm that is both predictable and complex, which the brain finds comforting. Each droplet follows natural patterns in timing, size, and sound, producing a subtle sequence that repeats but never becomes monotonous. This rhythm predictability allows the brain to recognize patterns without actively analyzing every sound. Predictable patterns signal safety, making it easier for the brain to relax. Unlike abrupt noises, such as a car horn or a door slamming, rainfall provides gentle variation within a consistent framework. This means the brain can settle into a rhythm, synchronizing its own neural activity with the sound. The steady, patterned sequence reduces mental effort, promoting focus, relaxation, or sleep. The predictability of rain is what makes it feel safe and soothing, creating an environment where humans can rest without constantly monitoring for danger. But why does rain feel safe rather than threatening in the first place? Rain feels safe instead of threatening because it rarely signals danger in nature. In human evolution, consistent rainfall was associated with nourishment, replenishing water sources, and fertile soil. Unlike sudden noises, which could indicate predators or immediate danger, rain is steady and predictable. Our brain recognizes the lack of unexpected spikes in sound or sudden movements and interprets this as a safe environment. The gentle patter of raindrops does not trigger the sympathetic nervous system, which handles stress responses. Instead, the parasympathetic system dominates, slowing heart rate and promoting calm. Rain provides a controlled, natural background that feels protective, as if the environment is stable and reliable. This safety perception is reinforced by the rhythmic, continuous sound that fills space without surprising the listener. The experience of rain as safe is deeply connected to its sound qualities, especially the absence of sudden, jarring noises. One key reason rain feels calming is the lack of sharp frequency spikes in its sound. Sharp spikes occur in sudden, loud noises like a clap of thunder or a dropped object, which trigger immediate alertness in the brain. Rain, however, produces smooth, continuous sound with overlapping frequencies, avoiding abrupt peaks. The energy in rainfall is spread evenly across high, medium, and low frequencies, creating a balanced, gentle acoustic experience. This absence of sudden changes allows the brain to relax instead of becoming hyperalert. Each raindrop contributes to a layered soundscape, but none creates a jarring spike. Even during heavy rain, the transitions are gradual, allowing our ears and nervous system to adjust naturally. This smooth frequency profile is why rain is often used in sleep aids, meditation recordings, and relaxation therapies. The continuous, spike-free nature of rain is essential for its calming effect on both mind and body. Rain produces a consistent acoustic distribution, meaning its sound energy spreads evenly across different frequencies and locations. Each droplet produces a tiny vibration, and together, millions of droplets create a continuous sound field that fills the environment. The result is a stable, layered soundscape where high, medium, and low frequencies are balanced, giving rain its characteristic soothing quality. Because the energy is spread evenly, there are no sudden loud peaks or gaps, which makes the sound predictable and gentle for the brain to process. This uniform distribution also creates a sense of space, allowing the listener to feel surrounded by rainfall. Even when drops hit different surfaces, leaves, soil, roofs, the overall sound remains coherent. This explains why rain can sound calm in a forest, a garden, or on a rooftop. But this consistent sound doesn't just feel relaxing, it also affects how we perceive other sounds in our environment. Rain acts as a natural environmental masker, meaning it can hide or reduce the impact of other background noises. Environmental masking occurs when one sound makes it harder to hear other sounds because it fills the acoustic space. In the case of rain, the constant patter of droplets produces a wide range of frequencies that overlap with noises like distant traffic, rustling leaves, or low chatter. Our brain focuses on the steady, predictable sound of rain and pays less attention to sudden or minor noises nearby. This masking effect makes the world feel quieter and safer, because abrupt or startling sounds are less noticeable. Many people use rain sounds in sleep machines for this exact reason. By covering up irregular environmental sounds, rain creates a calm, uninterrupted auditory experience. But the effect of rain doesn't stop at sound. It also interacts with our sense of smell in remarkable ways. Rain has a unique effect on smell that adds another layer to our experience of storms. When raindrops hit soil, plants, or concrete, they release microscopic compounds into the air. One of the most famous is petrichor, the earthy scent produced when oils from plants mix with water. Raindrops also dislodge small particles from surfaces and carry them into the air, allowing our noses to detect a fresh, distinct aroma. This smell is not constant. It becomes stronger as rainfall begins, when the first drops hit dry surfaces. The combination of scent and sound enhances the feeling of calm and refreshment, making rain a multisensory experience. Just as rain soothes with sound, it stimulates olfactory senses in a natural, non-threatening way. Experiencing the smell of rain is a signal of hydration, freshness, and life, completing the connection between the environment and human perception. Petrichor is the name given to the distinctive, earthy scent that rises when rain falls on dry soil or ground. It is a word scientists use to describe that fresh, calming smell we often notice at the beginning of rainfall. This scent is so strong and recognizable that many people associate it with cleanliness, renewal, or even comfort. Petrichor is created when compounds in the environment mix with raindrops and are carried into the air, making it easier for humans to detect them. Interestingly, this smell is not produced by the rain itself, but by what the rain interacts with, such as soil, plants, and tiny organisms. The first raindrops are usually the most effective at producing petrichor because they hit dry surfaces that have had time to accumulate these natural oils and compounds. This is why the smell of rain is often strongest at the very beginning of a shower. Plants play a key role in creating petrichor because they release oils during dry periods. Many plants secrete aromatic oils that coat their leaves, stems, and soil around them. These oils help the plants conserve water and protect themselves from bacteria and fungi while the environment is dry. When the first rain comes, these oils are dislodged by the impact of raindrops and enter the air as tiny particles, contributing to the fresh scent we recognize. This process is subtle but powerful, allowing humans to smell the rain even from a distance. The combination of plant oils and moisture signals the environment is replenishing itself, which may be why humans find the scent calming. These oils are just one part of the chemical mix that creates the multi-layered aroma of rain, complementing other natural contributors. Another major contributor to the smell of rain is a compound called geosmin, produced by soil-dwelling bacteria. Certain bacteria, like streptomyces, generate geosmin as part of their natural metabolic process. This compound has a distinct earthy odor that humans can detect even at extremely low concentrations. When raindrops hit soil, geosmin is released into the air along with plant oils, enhancing the overall scent of rainfall. The combination of geosmin and other compounds creates the unique petrichor smell that people associate with fresh rain. Geosmin is especially strong in soils that are rich in organic matter, which is why rain on farmland or forest soil smells particularly earthy. Without these bacteria, the smell of rain would be much less noticeable, showing how microscopic organisms contribute to a sensory experience that we often take for granted. Raindrop impact causes aerosolization, meaning it lifts tiny particles and compounds into the air, making the smell of rain detectable over a distance. When a drop hits the soil, it splashes and traps tiny droplets of water mixed with plant oils, geosmin, and other substances. These micro droplets become suspended in the air, carrying the smell upward. This process spreads the scent over a larger area than the point of impact alone. Aerosolization is also why the smell of rain can reach people before raindrops even touch them. The larger the raindrop and the drier the surface, the more particles are aerosolized. This interaction between water and natural compounds ensures that the aroma of rainfall reaches our noses efficiently, creating that fresh, earthy smell we instantly recognize. The impact of a raindrop, therefore, does more than wet the ground. It transports the very essence of rain into the air. Once raindrops lift scent particles into the air, these tiny molecules begin to travel through the environment. Wind, air currents, and turbulence help carry the particles away from the point of impact, spreading the smell over a wide area. Even a gentle breeze can transport the aroma of petrichor hundreds of meters from where the first drops hit. The lighter the particles, the higher and farther they can travel. Some particles stay close to the ground, adding a subtle scent as you walk through puddles or wet soil. Others rise and mingle with the air above, making the smell of rain noticeable even before the drops reach you. This widespread movement allows multiple senses to engage at the same time, hearing the rainfall while smelling it, creating a rich sensory experience. The travel of scent particles ensures that the familiar smell of rain is not limited to where the raindrops actually fall. Humans are highly sensitive to geosmin, the compound produced by soil bacteria that contributes to the earthy smell of rain. Even extremely low concentrations, just a few parts per billion in the air, can be detected by our noses. This heightened sensitivity allows humans to notice the scent of rain long before raindrops touch the ground. Scientists believe this sensitivity developed over time because recognizing the smell of water or moist soil was crucial for survival. Early humans could locate water sources or fertile land by following the smell carried by geosmin in the environment. Today, this sensitivity remains, triggering subconscious awareness of rain and fresh soil. It also enhances the calming effect of rainfall, as our brains associate the scent with safety and nourishment. Geosmin is therefore a tiny but powerful signal that deeply connects humans with the natural world. The calming effect of rainfall is reinforced by evolutionary associations that link petrichor and geosmin with survival. Historically, rain meant water was replenishing the environment, crops could grow, and rivers and ponds were full. Early humans would have associated these scents with abundance and safety. As a result, the brain learned to interpret the smell of rain as comforting and positive, signaling that the environment was favorable. This evolutionary comfort association continues today. Even if modern humans are far removed from survival needs, smelling rain triggers the same subconscious response: relaxation and a sense of security. This connection between smell and survival helps explain why people find rainy environments soothing. Beyond sound and scent, rain also brings another unique smell associated with thunderstorms. Before a thunderstorm, the air often carries the sharp, fresh smell of ozone. Ozone is a form of oxygen that forms when lightning splits oxygen molecules in the atmosphere. These molecules quickly recombine to create ozone, which has a clean, slightly sharp scent that is noticeable when the air is still before a storm. This ozone smell signals an approaching storm and often heightens awareness of changes in weather. Humans are particularly sensitive to ozone, even in small amounts, which may explain why the scent is so noticeable and often memorable. The combination of ozone with petrichor creates a multi-layered sensory experience, blending the earthy smell of rain-soaked soil with the crisp sharpness of atmospheric changes. This pre-storm scent alerts the senses, preparing both mind and body for the upcoming rainfall. Ozone's presence before a storm starts with the electrical splitting of oxygen molecules in the air. When lightning strikes, it produces a powerful burst of energy that breaks the bond between the two oxygen atoms in an O2 molecule. These free oxygen atoms are highly reactive and quickly combine with other O2 molecules to form ozone, O3. Ozone has a sharp, slightly metallic smell that humans can detect even at low concentrations. This process happens rapidly during electrical storms, producing enough ozone to be noticeable on the ground. The smell is most distinct just before rain begins because lightning often occurs in the early stages of a thunderstorm. This natural chemical reaction explains the unique pre-storm scent that people often describe as fresh or electrifying. Understanding the science behind ozone creation shows how raindrops, lightning, and air chemistry interact to give us a rich sensory experience, even before a single drop touches the ground. Before rainfall, humidity in the air usually rises noticeably. Humidity refers to the amount of water vapor in the air. As clouds build and moisture evaporates from surfaces, the air becomes more saturated with water molecules. This increase in humidity changes the way air feels, often making it heavier and more humid on the skin and in the lungs. High humidity can also enhance the smell of rain because water vapor carries scent particles like geosmin and plant oils more effectively. Even before raindrops fall, the rising humidity signals that a storm or shower is approaching. This change in the air's moisture content subtly prepares the body and mind for rainfall, creating an anticipation that many people feel as the first hints of rain approach. Humidity increase is therefore both a physical and sensory part of the experience of an incoming storm. Humidity changes how comfortable it feels to breathe. When the air is humid, it contains more water vapor, which keeps the mucous membranes in the nose and throat moist. This can make breathing feel smoother and more comfortable, especially for people in dry environments. On the other hand, very high humidity can make the air feel thick or heavy, which might feel slightly harder to inhale for some. The gradual rise in humidity before rain often produces a refreshing feeling because it moistens the airways and balances the temperature. In combination with the smell of petrichor and the sound of falling droplets, this effect adds to the overall comfort and relaxation associated with rain. Essentially, the humidity acts like a natural conditioner for the air, enhancing both respiratory comfort and sensory perception before the rainfall even begins. Drops in atmospheric pressure often signal that a storm is approaching. Air pressure is the weight of the air above a certain point, and when a storm forms, warm, moist air rises, reducing the pressure near the ground. Lower pressure allows clouds to grow taller and rain to form more easily. People may not feel the pressure change directly, but it can influence how the body feels, sometimes causing mild headaches, fatigue, or a sense of heaviness. Meteorologists monitor these pressure drops to predict storms and rainfall. When combined with rising humidity, darkening skies, and the scent of ozone decreasing pressure creates multiple indicators that a rainstorm is imminent. Understanding these signals shows that rainfall is part of a larger atmospheric system, with air, moisture, and electrical activity all interacting to prepare the environment for the coming shower. Changes in barometric pressure, which often occur before and during rainstorms, can have subtle effects on the human body. Barometric pressure is the weight of the atmosphere pressing down on the earth. When a storm approaches, the pressure drops, and the body senses this change in several ways. Some people experience mild headaches or joint discomfort because tissues and fluids in the body respond to lower pressure. Others may feel a sense of heaviness, fatigue, or slight changes in balance. The nervous system can also pick up these changes, making people more sensitive to environmental cues, such as temperature and humidity shifts. While most effects are mild, they are part of the reason why rainy days can feel different physically from sunny ones. This sensitivity to barometric pressure is another layer of interaction between humans and rain, showing how the atmosphere directly influences our physiology even before a single drop hits the ground. Rainstorms also generate negative air ions, which are electrically charged particles in the atmosphere. Negative ions are created when water molecules in the air break apart, particularly during rainfall, waterfalls, or waves. These ions attach to dust, pollen, and other particles, removing them from the air and improving overall air quality. The concentration of negative ions increases significantly during storms, especially in areas of active rainfall or near moving water. People often report feeling more refreshed or alert in environments rich with negative ions, although the exact physiological effects are still being studied. These ions are a natural consequence of rain interacting with the atmosphere, linking the physical process of precipitation to a subtle influence on the air we breathe. Negative ions add another sensory dimension to the experience of rain, complementing sound, smell, and humidity. During rainstorms, ion concentration in the air rises dramatically. Falling raindrops collide with molecules in the atmosphere, breaking some apart and creating free electrons. These electrons attach to oxygen molecules, forming negative ions. The more intense the rainfall, the higher the concentration of ions in the surrounding air. Locations near heavy showers, waterfalls, or moving rivers often have particularly high levels. These ions are believed to remove dust and allergens from the air by attaching to them and causing them to settle. While their exact effects on human physiology are still being studied, Areas rich in negative ions often feel fresher, cleaner, and more invigorating. This increase in ion concentration during storms shows how the physical dynamics of rain not only shape the environment, but also subtly alter the air quality and sensory experience for humans. The effects of negative ions on human mood are widely discussed, but still debated among scientists. Some studies suggest that exposure to high concentrations of negative ions can improve mood, increase energy, and even reduce feelings of depression. The idea is that negative ions may influence serotonin levels or oxygen absorption in the lungs, enhancing well-being. Other research finds minimal or inconsistent effects, meaning not everyone responds the same way. Despite this debate, many people report feeling mentally refreshed or calmer during or after rain when negative ion levels are high. Whether through chemical, neurological, or psychological pathways, ions add another layer to how rainfall influences human perception. This connection between rain, air ions, and mood illustrates the complex, multisensory impact of a natural event we often take for granted. Rain is not the same everywhere. It varies in intensity, size, and duration depending on atmospheric conditions and geography. Different types of rain are caused by the way clouds form, how moisture is lifted, and how air currents behave. Some regions experience light, steady rain, while others have sudden, heavy downpours. Even within a single storm, rain can vary, falling as tiny droplets in one area and larger, more intense drops nearby. Temperature, humidity, and wind patterns all influence rainfall characteristics. Mountains, coastlines, and urban areas can also change how rain behaves, concentrating it in certain places or dispersing it. Understanding that rain is not uniform helps explain why weather forecasts can vary so much over small distances. This variability sets the stage for exploring different types of rain, starting with the lightest form, which often feels almost gentle enough to ignore, but plays an important role in ecosystems and atmospheric processes. Drizzle is a very light form of rain, consisting of tiny droplets that fall slowly and gently. These droplets are much smaller than typical raindrops, usually less than 0.5 millimeters in diameter, and often feel like a mist. Drizzle forms when clouds are not very tall, and condensation happens gradually over a wide area. Because the droplets are so small, they can remain suspended in the air longer, and the falling water often evaporates partially before reaching the ground. Drizzle typically occurs from low, thick clouds and produces a soft, continuous patter rather than a loud rainfall. Despite being light, drizzle is important because it provides moisture to plants, soil, and the atmosphere without causing flooding. It also changes air humidity subtly, preparing the environment for heavier rainfall later. Drizzle demonstrates that not all rain is dramatic. Some forms are quiet, almost imperceptible, but still part of the water cycle. Stratiform clouds are the type of cloud most commonly associated with drizzle and light, steady rain. These clouds form in layers, covering large portions of the sky like a blanket. Unlike towering clouds, stratiform clouds do not rise very high into the atmosphere, which is why the rain they produce is usually light and continuous rather than heavy. Moisture condenses gradually within these clouds, creating small droplets that slowly fall to the ground. Because stratiform clouds cover wide areas, the rain or drizzle from them can last for hours, creating long, gentle showers. They often form when warm, moist air is lifted slowly over cooler air, or when a front passes through an area. These clouds are important in regulating ecosystems, providing steady water without the destructive effects of sudden storms. Understanding stratiform clouds helps explain why some rain feels persistent but gentle, unlike the more intense, short-lived rainfall from other cloud types. Convective rain, on the other hand, comes from clouds that form due to strong vertical air movements. Warm air rises quickly, carrying moisture high into the atmosphere. As the air cools, water condenses into larger droplets that grow rapidly. When the droplets become heavy enough, they fall as rain, often in short, intense bursts. Convective rain is responsible for thunderstorms and sudden summer showers. It tends to be localized, meaning heavy rain can fall in one area while nearby regions remain dry. These storms often produce larger droplets, strong winds, and sometimes lightning. Convective rain is driven by energy in the atmosphere, and the rising air is key to forming the dramatic, rapid rainfall associated with it. This contrasts sharply with the gentle drizzle from stratiform clouds, showing that rain comes in many forms, each shaped by unique atmospheric dynamics. Cumulonimbus clouds are the giants of the sky, responsible for the most dramatic and intense rainfall. These clouds form when warm, moist air rises rapidly in the atmosphere, carrying water vapor high into cooler regions. As the air cools, condensation occurs and droplets combine into larger and larger drops. Cumulonimbus clouds can grow very tall, sometimes up to 12 kilometers, reaching into the upper atmosphere. Their height and density allow them to produce heavy rainfall, strong winds, hail, and even lightning. The vertical motion within the cloud keeps droplets suspended long enough to grow very large before falling. Because of their size, cumulonimbus clouds can cover a large area while also producing localized bursts of rain that are extremely intense. These clouds form mainly in unstable atmospheres, often in warm climates or during summer afternoons. Understanding cumulonimbus formation explains why thunderstorms can be sudden, powerful, and highly localized, contrasting sharply with gentler types of rain like drizzle. Tropical rainfall is known for its intensity and volume, often far exceeding what is typical in temperate regions. In tropical climates, the air is warm and carries high amounts of moisture, which fuels frequent and heavy rainstorms. When warm, humid air rises quickly, it condenses into large droplets, often producing torrential downpours. Rainfall in the tropics can be extremely short but very powerful, sometimes releasing several centimeters of water in just an hour. This intensity is amplified by consistent heat from the sun and abundant water sources like oceans and rivers. Tropical rain is also influenced by large-scale atmospheric circulation patterns, which bring moisture-laden winds across the region. This type of rainfall supports lush vegetation, dense forests, and vibrant ecosystems, but it can also lead to flooding and erosion in certain areas. The extreme intensity and regularity of tropical rain make it a unique and vital part of Earth's water cycle. Monsoon systems are seasonal wind patterns that bring heavy rainfall to specific regions, particularly in South and Southeast Asia. During monsoons, winds change direction between seasons, carrying moist air from oceans over land. In summer, warm land surfaces cause air to rise, drawing humid winds from the ocean, which results in widespread, intense rainfall. In winter, the winds reverse, often bringing dry air back toward the ocean. Monsoons are not just about rain. They are massive atmospheric systems that shape climate, agriculture, and ecosystems across large areas. Their timing, intensity, and duration are critical for crop growth and water supply. These seasonal winds rely on temperature differences between land and sea, demonstrating how global and local atmospheric processes combine to create predictable yet powerful rainfall events. Monsoon systems highlight how rain is not just local. It can be driven by vast patterns across continents and oceans. Seasonal wind reversal is the underlying cause of monsoon systems and explains why rain arrives in distinct periods. During summer, land heats up faster than the ocean, creating low-pressure zones over continents. Warm, moist air from the ocean flows inland to fill this low-pressure area, rising as it warms and forming rain-producing clouds. In winter, the land cools faster than the ocean, reversing the pressure difference. Winds shift direction, often bringing dry air from land toward the sea. This reversal happens consistently every year, which is why monsoons are predictable. Seasonal wind reversal demonstrates the connection between temperature, pressure, and rainfall. It shows that rain is not just a result of local clouds, but part of a larger climate system shaped by energy from the sun and the differences in heating between land and water. Understanding this process helps explain the rhythm and timing of rainy seasons in many parts of the world. Orographic rainfall occurs when mountains force moist air to rise, cool, and release precipitation. As wind carries humid air toward a mountain range, the air is pushed upward along the slopes. Rising air cools at higher altitudes, causing the water vapor to condense into clouds and eventually fall as rain. The windward side of the mountain receives heavy rainfall, often creating lush forests and rich vegetation. This type of rainfall is common in areas where mountains meet oceans, such as the western coasts of continents. The process also affects local climate, temperature, and ecosystem development. Orographic rainfall demonstrates how the shape of the land influences weather patterns. It is different from rain caused by frontal systems or convection, because the mountain itself acts as a barrier, triggering precipitation. The interaction between air, moisture, and terrain creates distinct patterns of rain distribution, making some areas wet and others surprisingly dry. The rain shadow effect happens on the leeward side of mountains, opposite to where orographic rainfall occurs. After air rises over a mountain and drops its moisture on the windward side, it descends on the other side. Descending air warms and becomes drier, making rainfall much less likely. This creates arid or semi-arid regions called rain shadows. Many deserts around the world, like the Atacama Desert in Chile, exist because of this effect. The rain shadow demonstrates how mountains can create sharp contrasts in rainfall over short distances. Even though clouds may form nearby, areas in the rain shadow remain dry. This effect is a reminder that rain is not only about clouds and humidity, it is also about geography. Mountains shape how water moves through the atmosphere and determines which regions become lush and which become dry. Understanding this explains why rainfall can vary dramatically in seemingly close locations. Acid rain is a type of precipitation that occurs when rainwater combines with pollutants in the atmosphere, such as sulfur dioxide and nitrogen oxides. These chemicals are released from human activities like burning fossil fuels in factories, power plants, and vehicles. When they dissolve in water droplets in clouds, they form weak acids like sulfuric acid and nitric acid. As a result, the rain that falls from these clouds becomes acidic rather than neutral. Acid rain can harm plants, soil, and aquatic life by changing the natural pH balance of ecosystems. It also erodes buildings and monuments made of limestone or marble. Acid rain demonstrates that rain is not always purely natural. It can carry the imprint of human activity. Despite looking and feeling like normal rain, it can have long-term environmental consequences. Understanding acid rain highlights the delicate balance between atmospheric chemistry and rainfall. Acid rain forms because atmospheric pollutants dissolve in water droplets during condensation. Sulfur dioxide and nitrogen oxides mix with water molecules in clouds to create tiny acidic droplets. As clouds continue to form and droplets grow larger, the acidity is carried with the water. When these droplets eventually fall to the ground as rain, snow, or fog, they release the acids into the environment. The process shows how gases in the atmosphere can chemically interact with water, altering its natural composition. Even though the acidity is usually weak, repeated exposure can change soil chemistry, damage vegetation, and affect freshwater ecosystems. Pollutants can also travel long distances, meaning acid rain can affect areas far from the original source. This demonstrates that rainfall is not only a local phenomenon, but also connected to global air quality and human impact. The chemistry of rain is more complex than it appears, combining natural processes with environmental changes caused by humans. Clean rain and polluted rain differ in both composition and impact. Clean rain forms when water vapor condenses in the atmosphere without significant interference from pollutants. It contains mostly pure water, small amounts of natural dust or salts, and is neutral in pH, usually around 5.6. This type of rain nourishes plants, replenishes water sources, and supports ecosystems without harmful effects. Polluted rain, on the other hand, forms when human-made or natural pollutants like sulfur dioxide, nitrogen oxides, or industrial particles mix with rainwater. These chemicals dissolve into the droplets, making the rain acidic and potentially harmful to plants, animals, and human structures. The difference is subtle visually. Both look like ordinary rain, but the chemical composition changes everything. Clean rain supports life and maintains environmental balance, whereas polluted rain can slowly damage ecosystems and infrastructure. Understanding the distinction emphasizes that rainfall is not always purely natural. It can carry a record of human impact on the atmosphere. Freezing rain is a rare and fascinating type of precipitation that occurs when raindrops fall through a layer of cold air near the ground. Unlike normal rain, these drops do not freeze while falling through warmer layers of air higher up. Instead, they remain liquid, even though the surface temperatures below are below freezing. When the supercooled droplets touch cold surfaces, like roads, trees, or cars, they instantly freeze, forming a coating of ice. This makes freezing rain particularly dangerous because it can create slippery roads, damage trees and power lines, and produce hazardous conditions almost immediately. It often occurs during winter storms when a layer of warm air sits above a shallow layer of freezing air near the ground. Freezing rain shows that even ordinary raindrops can behave differently depending on temperature layers in the atmosphere. The phenomenon is a reminder of how delicate temperature changes in the air can dramatically alter the type of precipitation that reaches the surface. Supercooled droplets are raindrops that remain liquid even though they exist at temperatures below 0 degrees C, 32 degrees F. This happens because the droplets lack a nucleus, like dust or ice crystals, to start the freezing process. They are essentially cold but not frozen, carrying the potential to freeze instantly if they encounter a suitable surface. Supercooled water is highly unstable, and the moment it contacts a solid object below freezing, it forms ice immediately. These droplets are the key ingredient in freezing rain, as they fall through cold layers without solidifying. The existence of supercooled droplets demonstrates that the freezing point of water can be influenced by environmental conditions and impurities. Understanding this process explains why winter precipitation can take unusual forms, from freezing rain to sleet, and why ice can form so suddenly during storms. Supercooled droplets reveal how raindrops can behave in surprising ways depending on atmospheric temperature and surface conditions. Sleet forms when raindrops pass through a layer of cold air on their way to the ground and freeze before hitting the surface. Unlike freezing rain, sleet becomes solid before landing, turning into small, translucent ice pellets. This happens when a warm layer in the atmosphere allows rain to form initially, but a thicker cold layer below forces the drops to freeze completely. Sleet bounces slightly when it hits the ground and does not form a glaze of ice like freezing rain, but it can still create slippery conditions. It is common during winter storms where temperature layers are uneven, producing mixed precipitation. Sleet illustrates how temperature variation in the air column can change the form of precipitation dramatically, even over short distances. By studying sleet, meteorologists can predict hazardous winter conditions and understand how raindrops interact with cold air layers. This shows once again that rain is not just one simple form. It adapts to environmental conditions in multiple ways. Hail forms through a complex cycle within strong thunderstorms, creating ice balls that can range from tiny pellets to large, dangerous stones. It begins when raindrops or supercooled water droplets are caught in powerful updrafts inside cumulonimbus clouds. The droplets are lifted high into extremely cold regions of the atmosphere, where they freeze solid. Once frozen, the small hailstones can be carried upward again by the storm's strong upward winds, collecting additional layers of water that freeze on contact. This cycle may repeat several times, causing hailstones to grow larger with each pass through supercooled water layers. Eventually, the hail becomes too heavy for the updrafts to support, and it falls to the ground. Hail formation demonstrates how dynamic and powerful storm systems can be, combining temperature, wind, and moisture in a dramatic process. Unlike ordinary rain, hail represents a violent but fascinating interaction between atmospheric forces and water droplets in extreme conditions. Strong updrafts are essential for hail formation because they carry droplets high enough to freeze in the colder regions of the cloud. The faster and stronger the upward wind, the larger the hailstone can grow, as it can repeatedly cycle through layers of supercooled water. Without a strong updraft, hailstones would fall too quickly before accumulating multiple layers, producing only small ice pellets or ordinary frozen rain. Updrafts create turbulence that allows droplets to collide with supercooled water, promoting layering and growth. They also help keep the developing hail suspended long enough to gather significant mass. Meteorologists can estimate storm severity by analyzing updraft strength, as stronger updrafts correlate with the potential for larger, more damaging hail. Understanding the necessity of updrafts shows how gravity, wind, and temperature interact to produce one of the most extreme types of precipitation, distinct from drizzle, rain, or sleet. Hailstones develop layers because of the repeated cycling through different temperature and moisture zones within a storm cloud. Each time a hailstone is lifted by the updraft into a supercooled region, it accumulates a thin layer of ice as water freezes onto its surface. When the hailstone falls slightly or is carried to warmer parts of the cloud, the ice layer may partially melt before being lifted again. This process creates concentric layers, much like rings in a tree trunk, which indicate the hailstone's growth history. Larger hailstones usually have more layers, showing multiple trips through freezing and thawing regions. Studying the layering can reveal the strength and dynamics of the storm, including updraft intensity and cloud structure. The layered structure also affects how hail behaves when it hits the ground, including its hardness and potential for damage. Hail layers are thus a record of the storm's internal movements and temperature fluctuations. Rain's importance is not limited to storms or weather patterns. It is a critical component of Earth's global system. Rain replenishes rivers, lakes, and aquifers, providing water for drinking, agriculture, and industry. It supports ecosystems by nourishing plants, which in turn sustain animals and humans. Rain also plays a vital role in regulating temperature and humidity, influencing climate and weather patterns worldwide. Through the water cycle, rain redistributes moisture from oceans to land, balancing water availability across the planet. Without rain, many regions would become deserts, and life as we know it would struggle to survive. Rain also interacts with the atmosphere to clean air, support plant growth, and even influence human health and mood. From gentle drizzles to powerful tropical storms, rainfall connects weather, ecosystems, and human societies in a continuous, vital cycle. Its global importance makes rain one of the most essential and fascinating natural phenomena. Rain plays a crucial role in replenishing freshwater sources on Earth, which are essential for all life. When rain falls, it collects in rivers, lakes, and reservoirs, restoring the water that has evaporated, been used for irrigation, or consumed by humans, animals, and plants. Freshwater replenishment is part of the larger water cycle, where precipitation, evaporation, and condensation work together to maintain a balance. Without regular rainfall, freshwater sources would shrink, leading to droughts and scarcity. Rain also dilutes pollutants in rivers and lakes, helping maintain water quality. In agricultural regions, replenished water allows crops to grow and ecosystems to thrive. The continuous input of rain ensures that humans and wildlife have access to clean water, supporting life in a sustainable way. Every shower, drizzle, or downpour contributes to this vital process, highlighting the unseen importance of rainfall in sustaining our freshwater systems. Groundwater recharge is another critical way rain supports life on Earth. When rainwater soaks into the soil, it percolates down through layers of earth and rock, eventually reaching underground aquifers. These aquifers store water that can be used for drinking, agriculture, and industrial purposes. The process of infiltration depends on soil type, vegetation, and terrain. Sandy or porous soil allows water to seep faster, while clay or compacted soil slows it down. Recharge replenishes these hidden reservoirs, which can supply water during dry periods when surface water is limited. Without rain, groundwater levels drop, leading to wells drying up and ecosystems suffering. Groundwater recharge demonstrates that rain's impact extends beneath the surface, silently sustaining life even in areas where water may not appear abundant. It is a hidden but essential part of the water cycle, keeping the planet hydrated. Rain feeds river systems, creating a network of waterways that distribute freshwater across continents. When precipitation falls over land, some water flows directly into streams and rivers, while some infiltrates the ground to join aquifers. Rivers rely on consistent rainfall to maintain flow, support aquatic life, and provide water for human use. Seasonal variations in rain influence river levels, sometimes causing floods or droughts depending on intensity and timing. Rain also transports nutrients from the land into rivers, supporting ecosystems along the way. Snowmelt and rainfall work together in many regions to sustain rivers year-round. Without rain feeding rivers, these waterways would shrink or disappear, affecting plants, animals, and human communities that depend on them. Understanding how rain sustains river systems highlights the interconnectedness of precipitation, land, and life, showing that each drop contributes to a much larger planetary network. Every drop of rain you hear tonight is part of a planetary system billions of years old, silently working above and around you. From evaporating oceans to clouds forming high in the atmosphere, from tiny droplets colliding to rivers and aquifers filling, every raindrop is a piece of the Earth's ongoing water cycle. It connects mountains, forests, deserts, and cities in an intricate system that has been repeating for eons. The sound of rainfall is not just a momentary sensation. It is evidence of Earth's continual renewal, carrying moisture, energy, and life across the planet. Each drop interacts with the air, soil, plants, and humans, quietly sustaining ecosystems and maintaining balance. So, as you listen to rain tonight, remember that you are experiencing a process that is ancient, global, and essential. It is a reminder of Earth's delicate and powerful natural systems, happening quietly, yet profoundly, above you right now.